Good morning, everyone. It's my pleasure to attend the 18th IEEE MCSoC 2025 conference today. My name is Yawei Chen from the China Resources Microelectronics Limited. I'm the manager of Yield Enhancement Department. My paper title is an Ensemble virtual metrology model of machine learning in semiconductor manufacturing. This paper is divided into 6 parts: introduction, literature review, methodology, results, discussion, conclusion, and future works. As AI advances and semiconductor manufacturing grows more complex, virtual metrology has become a cost-effective alternative or complement to traditional physical metrology, crucial for yield management and quality control. VM predicts the wafer properties using process equipment sensor data with minimal latency, eliminating the need for physical measurement. There are two challenges. One is predictive accuracy. The other is integrated system that cooperates with the semiconductor MES system. The tree-based model addressed the challenge of improving predictive accuracy for thickness measurement. This study develops the Ensemble machine learning framework, combining RF and XGB algorithm to achieve an R-square of 98.28% and reduce the low yield wafer excursion by over 80%. It is applied to LPCVD nitride film process in real-world environment and presents an embedded system with low latency, self-training corrections, automatic verification, and a flexible sample rate for both physical and virtual metrology. Summary of virtual metrology technologies in manufacturing applications. We can see the subcategories: semiconductor manufacturing, application in CVD and PVD processes. The mainstream research directions is decision tree based and neural networks models applications. Summary of machine learning algorithm models for semiconductor manufacturing. We use the RF and XGB models, which are medium complexity, little training time, better interpretability, and higher accuracy and faster speed. Due to hardware limitations, particularly with GPUs, a trade-off must be made between hardware configuration and algorithm selection. This page illustrates the Ensemble decision tree-based model framework for virtual metrology, including the input data preprocessing, Ensemble algorithm, and output modules. To improve prediction accuracy, robust Ensemble algorithm that capture the nonlinear feature of process signals can be developed by the leveraging domain expertise and data analytics. The LPCVD furnace to a sensor data must be collected via the FDC system, which includes 18 process parameters such as reaction gas flow from the FFC, process pressure, temperatures, and process time. The nitride layer applied over 5 times commonly serves as an edge stop or gate spacer to improve the lightly doped drain region characteristics. Is the key process in semiconductor manufacturing. We propose a decision tree-based ensemble model combining RF and RGB to predict the thickness of thick and thin nitride fins in LPCVD process. Modeling employed 80% of 2,200 real-world samples for training and 20% for validation. From 18 process parameters, the top 9 key parameters were selected based on the correlation heat map with prediction values. Virtual metrology achieved R-square 98.28% for 1,500 angstrom thickness, outperforming single models. Proposed model used 7-fold cross-validation test, R-square performance, and the confidence interval R-square is from the 98.8% to 98.46%. This picture illustrates the virtual metrology system used in semiconductor real-world environment. When the RI below 90%, promoting an automatic feedback signal to training module. If the VM data falls outside of the specific limits, system will automatically instruct the production equipment to block the process tool. Meanwhile, the system will automatically issue an instruction to the metrology sampling system for physical metrology verification and establish a flexible sample rate for both physical and virtual metrology. The impact loss of excursion cases reduced by over 80% from a healthy process equipment as the VM achieves full coverage of every wafer without any latency in queue and runtime during physical metrology. This model also can be used on other chamber types thin film processes, batch type diffusion, and wet cleaning process prediction such as thickness, concentration, depth, and etch rate. This approach is better suited for lightweight data volumes and nonlinear feature dataset. For computational efficiency, Ensemble machine learning models can be run on CPUs without GPU acceleration. For processing fewer than 100 parameters using decision tree-based machine learning models, a configuration of CPU is recommended. NM models still rely on GPU acceleration due to their relatively higher complexity, longer training times, and lower interpretability. Therefore, it is essential to balance accuracy, efficiency, interpretability, and cost depending on specific purpose, whether for dry runs or mass production environments. This finding offers a new perspective for improving the accuracy of virtual metrology thickness prediction in semiconductor manufacturing, specifically in LPCVD process applications. Future study could explore a vision model that leverages large language models and deep learning techniques to develop an agent client that enhances accuracy. It offers a low-cost, high-precision, and rapid process solution to practitioners. That's all. Thank you.